Welcome back, guys. In this video, we'll be taking a look at simple harmonic motion. And if you recall from class, simple harmonic motion arises when you use Hooke's force law in Newton's second law. And then solving this equation produces oscillatory motion. In other words, things are bouncing back and forth with the frequency that depends on two quantities. It depends on how stiff the spring is, which is given by this quantity k, and also how much mass you have attached to the spring. So let's go ahead and take a look at a problem illustrating this concept. Okay, so in this scenario, we have three cars attached to this cable. And this cable kind of acts like a spring in the sense that the more weight you put on the cable, it'll stretch out, just like any sort of thing that follows Hooke's law. Now, what happened in the situation is that these cars are originally sitting here in equilibrium, but then the bottom one somehow detaches, and the remaining two cars, because this is basically a Hookean spring, these two cars start to execute simple harmonic motion, oscillating back and forth. The question is, at what frequency do they oscillate? And then how big is the oscillation? So first, let's talk about the frequency. As I noted, the frequency will depend on two quantities: how stiff the spring is and how much mass is attached to the spring. Now, let's talk about the mass first. So right now, we have three cars attached to the cable. But that's not the mass we should use, because right now nothing is executing simple harmonic motion. That doesn't happen until the bottom one detaches. So when you actually have the oscillating system, that only has two car masses on it. So the mass for the oscillatory motion is 2 times mc, where mc is just the mass of one of the rail cars. Okay, so that's pretty straightforward. Now we also need the spring constant. And that's not given explicitly in the problem. But what we're going to do is the following. We're actually going to analyze the system before it detaches. And the reason is that the spring constant is a material property. So it's a constant for this cable, and it doesn't matter what's attached to it. K will always be K, no matter what's attached to it, how it's moving. The reason we want to use the situation before the car detaches is that in that situation, everything is in equilibrium, so the acceleration is 0. In other words, we can use Newton's second law, balance the forces, and we don't need to know the acceleration. Or I guess we don't need to use the acceleration because it just drops out of the equation. So what we're going to do here is draw a free body diagram, determine all the forces upon this oscillating system as it's oscillating, or sorry, the equilibrium system before it starts oscillating. And you'll find out when you do that, everything will cancel out except for the spring constant. So go ahead and do that now. Just draw a free body diagram, label all the forces, decompose the forces into the correct directions, and solve for k. And before you do that, let me just go ahead and mention that, of course, the most useful system to use is a coordinate system that looks like that. So go ahead and take a look. Go ahead and do that. We'll take a look when we come back. OK, so writing the free body diagram for the situation, we have a couple of forces. We have the force of gravity pulling it down, which is mg. We have the force of the cable, which is following Hooke's law. So that's going to be k delta x. The force depends on how much it's stretching out. And those are the only two forces. We also have the normal force. Let me go ahead and write that on there. All right. And so remember from physics 2a that if we want to solve this type of situation, we have to decompose all the forces into perpendicular directions. So these guys are already in the axes we want, but we have to decompose mg. And since we're only wondering about what this quantity is, I'm just going to worry about the x component. And this is something you've done in physics 2a many times. So using trigonometry, we find that this component is mg sine theta. Finally, plugging in these forces in Newton's second law, you find that, well, this one is in the negative x direction. This one's in the positive x direction. So you have minus mg sine theta plus k delta x equals 0. Now the question is, what do we have here? We have delta x, we have theta, we know g. We're looking for k, but we don't have the mass. Well, in this case, the mass, is it 2 cars or 3? It's 3 because we're analyzing the situation before the bottom car broke off, when it's in equilibrium as these 3 cars are sitting there. So this m is going to be 3 times mc. All right, so you're going to have minus 3 mc g sine theta plus k delta x equals 0. And then inverting this equation, you're going to find that k equals 3 times the mass of the rail cars times g times sine theta. And then you're going to divide that by delta x. And all these quantities are known. So you can solve for a k, giving the numbers you're given. And then what we're looking for originally was the frequency of the harmonic motion. What we needed were m and k. We have mass, we have k. So you can plug in these two quantities into this formula, and you'll find that the frequency is 1.1 hertz. Okay. In other words, this harmonic motion will continue at a rate of a little more than 1 cycle per second. Okay, so it's a little faster than 1 cycle per second. Now, the second part of the question asks, what is the amplitude of that motion? In other words, how much is it going from its furthest point to its closest point? So let me write that up here. The amplitude is what we're looking for next. Well, to analyze this, let's start first with a little bit of physical intuition. When the bottom car breaks off, these two cars are about to move upward, but they're stationary. They're at 0 velocity. Okay, so the bottom car breaks off. These guys momentarily are stationary and then start moving upward. And then they go up until the spring has compressed, and then it'll go back down. Okay, so these guys just kind of go back and up and down like this. But where they start is at a point of 0 velocity. And remember, the points of 0 velocity are either the furthest point of the spring or the closest point of the spring. So this is obviously, we're starting at the furthest point of the spring. So in other words, this harmonic motion will have a max amplitude, or a max extension of 15 centimeters. All right. Now, if we knew how far it compressed, we would be able to find the amplitude. That would be twice the amplitude. But we don't know that quantity. However, we can just use the fact of, well, the equilibrium point, because that's actually equal to 1 amplitude. The distance from its furthest extension to its equilibrium point is 1 amplitude. So what we can do here is find the equilibrium point when there's only 2 cars attached to that cable. And we did that a minute ago. But in that case, we did it when we had 3 cars attached to the cable. So to find the amplitude here, what we're going to do is the following. We're going to use the fact that the max extension is 15 centimeters. And we're going to find the equilibrium point using a very similar process to what we did a moment ago, balance of forces. So go ahead and do that now. Find out what the equilibrium extension is, and then subtract it from 15 centimeters to get the amplitude. Take a minute to do that now. We'll come back and take a look. OK, so for the equilibrium point, it's going to be very similar to what we did a minute ago. We found the equilibrium point, and to do that, we had developed this equation right here. But the difference was, in that case, we were to find the equilibrium point when there was 3 cars attached to the cable. Now we're looking for the equilibrium point if there's only 2 cars attached. So we're going to get a similar equation to this. And if you invert this, but now we're solving for delta x, not for k. Remember, we found k, and k doesn't change. So if we invert this for delta x, we find that delta x equals mg sine theta divided by k. And then in this case, the m is just 2 rail cars. So it's going to be 2 times mc times g sine theta divided by k. Plugging that in, you'll find that that equals 0.1 meters. And so that means that the amplitude is going to be the furthest extension, which we had intuited a moment ago was 15 centimeters, minus the equilibrium extension, which is 10 centimeters. And so that means that the amplitude is 5 centimeters. OK, so this answers the first 2 parts of the question. The last part of the question is, what would be different if instead of having the bottom rail car move off, if we had the bottom 2 rail cars detached from the top one? In other words, out of the following 3 quantities, so instead of 1 car, we have 2 detached. What changes out of these following 3 quantities? Quantities are the frequency, the spring constant, and the amplitude. Do they change? And if they do change, are they bigger or smaller? So we've already done these problems. You should have developed some intuition about how these things are related to how much mass is attached to them. So go ahead and try these on your own. Figure out whether they change, and if they do, how much, or if they're bigger or smaller just qualitatively. And we'll come back and take a look. So as I discussed a few times, the spring constant is not going to change. It's a material quantity that doesn't change no matter how much mass you have attached to this cable or anything. So k is going to be the same. And that's the first thing we can use. So now that we know that the spring constant is constant, well, by its very definition, then we can use this equation to determine how the frequency changes. We know that k is the same, but m is going to be smaller because we only have 1 cable car attached to that cable. So if m goes down, then the frequency has to go up. So, and this is kind of intuitive. If you had if you can just kind of imagine physically what would happen if those bottom two cars attached, this thing would fly up much quicker, it seems like, because you have a smaller mass attached to it. It's like when you attach a small mass to a spring, it'll start to move up in a much easier fashion. So the frequency will be higher. And the last thing is the amplitude. We noted that the amplitude was found in our last case by subtracting the equilibrium distance from the original distance. How does the equilibrium distance change? Well, it depends on the mass, and if the mass goes down, then we're going to have a smaller equilibrium distance. In other words, it's starting at 15 centimeters, but then it's going to have to travel a further distance to get to its equilibrium, so the amplitude is bigger. Okay. So in this case, when you have only one rail car attached to that, after those bottom two fall off, it's going to oscillate at a much higher frequency, and it's going to go in a much larger trajectory. In other words, it'll cover more ground. All right, so that's the problem. In this case, for the entire problem, basically we were analyzing simple harmonic motion, looking for the frequency of the harmonic motion, and then looking for the amplitude of the harmonic motion. And finally, we analyzed what would happen qualitatively if some of these features had changed. So I'm going to leave you with a summary, and we'll see you next time.